The fact that we can no longer talk about the atom and electrons in the atom as a small version of what we can actually see in the large world leads us to a new model of the atom. Quantum mechanics, the current model of the atom. Quantum mechanics is sometimes called wave mechanics. It was developed by many scientists over the course of about 20 years. Here are the two basic points of quantum mechanics. 1. Only certain energies are allowed for an electron in an atom. 2. Electrons are in orbitals in the atom. The basic idea is that we need to treat electrons as waves in the atom. In order for an electron wave to remain in the atom, it must be what is called a standing wave, that is, one that does not travel through space. We call this non-moving wave an orbital. What is an orbital? If we imagine a bee flying around a flower, and we take pictures of the bee as it flies around the flower, we can plot the position of the bee at various times. We might get a plot that looks something like this, where each of the dots represents the position of the bee in one of the pictures. If we remove the flower and look only at the positions of the bee, we would see something like this. This is what an orbital might look like. We have a particular shape, in this case it looks sort of like a flower, which shows where we are most likely to find the bee over time. Here is the definition of an orbital: a region in space where an electron is likely to be found. Quantum mechanics and the quantum numbers. One of the most important scientists in the development of the quantum mechanics was a German scientist named Erwin Schrödinger. He developed a mathematical approach to the electron being both a wave and a particle that is called quantum mechanics. In quantum mechanics, we treat the electron as a standing wave. This treatment results in the quantization of the energy of the state of the electron in the atom. In addition to the energy being quantized, the mathematics produces what is called a wave function that describes the location of the electron wave in space. This mathematical function ends up having certain physical properties that come out of the mathematics. Among these properties is one that relates the probability of finding an electron to the square of the value of the wave function at any point in space. The mathematics of solving Schrödinger's equation gives rise to a set of wave functions, mathematical functions in x, y, and z, that are the orbitals of the atom. Each orbital describes the distribution in space of the electron density when an electron occupies that orbital. Each orbital is described by a set of 3 numbers called quantum numbers. The first quantum number is called the principal quantum number and is represented by the letter n. The number value of n is related to the energy level of the orbital and so describes the energy and size of the orbital. N takes on integer values greater than 0. Each atom has all possible values of n, from 1 to infinity. The second quantum number is the azimuthal quantum number and is represented by the letter L. The number value of L defines the shape of the orbital, and if more than one electron is present in the atom, it also describes something about the energy of the orbital. The values of the azimuthal quantum number depend on the value of n, and are whole numbers ranging from 0 to n-1. This means that for any particular value of n, there are n different values of L. In order to avoid confusion with the number values of n, we typically use letters to represent the different values of L. The first 4 letters used are shown here. S-type orbitals have L equals 0. P-type orbitals have L equals 1. D-type have L equals 2. And F-type have L equals 3. After F-type, the letters go up the alphabet, but we seldom need to go much beyond F-type orbitals to describe electrons in the atom. The third quantum number is the magnetic quantum number, represented by M with a subscript L. M sub L describes the orientation of the orbital in space. M sub L has values that depend on the particular value of L, and are integers which range from -L to +L. In a particular energy level, that is, all orbitals with the same value of n, there can be at most 1 s-type orbital, 3 p-type orbitals, 5 d-type orbitals, 7 f-type orbitals, and so on. This table shows the possible combinations of the 3 quantum numbers. Remember that each unique combination represents a specific orbital in the atom. All the orbitals with the same value of n are a shell. The shells are called by numbers, specifically the value of n. So we have the first shell, the second shell, and so forth. Each different value of L within a shell is a different subshell. The subshells are identified by the letters of the L values. So we have S subshells, P subshells, D subshells, F subshells, and so on. The subshells are identified by the shell number and the letter for the type, like 1S, 2P, 4D, and so on. The number is the shell, and the letter is the type of subshell. Each different value of M sub L within a subshell represents a specific orbital in the subshell. So, as you can see, every S-type subshell has 1 orbital. Every P-type subshell has 3 orbitals, and so on. A 4th quantum number was added in the 1920s when it was discovered that 2 electrons in the same orbital do not have exactly the same energy. This is the spin quantum number, M with a subscript S. The spin is really talking about the magnetic field of the electron, which affects the energy. M sub S can have only 2 values, +1/2 and -1/2. This leads us to the Pauli exclusion principle. We all know that 2 objects cannot occupy the same space at the same time. For electron waves in an atom, this is the equivalent of saying that 2 electrons in an atom must have different energies. Since the energy of an electron wave is described by the 4 quantum numbers, this means that 2 electrons in an atom cannot have identical sets of quantum numbers. This is the most complete statement of the Pauli exclusion principle. In addition, since the first 3 quantum numbers identify an orbital, and the 4th can have only 2 possible values, this also means that at most 2 electrons can occupy an orbital. So here is a table that shows both the number of orbitals in each of the subshell types and the maximum number of electrons each type of subshell can hold. For any specific type, we can find the number of orbitals by multiplying the number value of L by 2 and adding 1. The maximum number of electrons is then twice that number. If you would like to copy this table, you can pause the video here.